Hi, good morning. Before we go to the class, I wanted just to make an announcement that I have posted a grade estimate on Blackboard. Just wanted to explain briefly what each of the column means, okay? So on Blackboard, you will see that you have a column called the pre-flight average. So those are the pre-flights using the first, I believe, first 9. And as we have more coming, of course, at the end of the semester, those scores will be updated. But those averages are based on the first 9, and I dropped the lowest 2. And there is another column called the, so I got a question, how do I calculate pre-flight grades? As long as you did it, it does not count for correctness or accuracy. Just as long as you did it, you get full credit. Okay, and another column called the homework average. So homework scores are based on the first 8 set, and then lowest 2 of those 8 are dropped as we have more homeworks grades coming in, and those score will be updated as well. Okay, so pre-flight 5%, homework 20. So if you see anything that is not correct with your pre-flight or homework, make sure you let me know. I just recently did a update on the score. So if you're still seeing a wrong score, please let me know, but you can check it now. I just recently did an update. Okay, and then there is another column called exam 1 out of 100. So that's the percentage, right? If you got 70%, that it will be 70 out of 100 points. So that's your exam 1 score. Exam 2 is, again, you already see your exam 2 previously, but now I added another column, exam 2 out of 100. That's your exam 2 score. Okay, each of those counts for 20%. And then we also did the at the beginning of the semester, we have a pre-assessment. As long as you did that assessment, you get 1 extra point, 1%. So that is show us as 1 if you did it. So all of those add up to be, okay, 5% of pre-flight, 20% homework, 20% of each exam, add 1 extra credit. Those are added to be what's showing up as your accumulated grades so far. You can see those are out of 65 points total, because the final exam is 35%. So all we have done so far is out of the 65% total. Now you can work with that and set up a goal for yourself, saying, okay, if I get this on the final, what would that give me for my total grade? So I did one example for you. So I put, okay, if you get a 65 on the final exam, which is according to the current grading scale and syllabus, is a C-. So if you want to obtain a C- in the final grade, how much do you need on the final? So then that column show you how much you will need. But again, it's
Dr. Ryan?
Yes?
I just want to confirm that's a percentage, right?
Yeah,
like you need that percent.
Yeah, it's
Okay.
up. Yeah, I didn't take the percentage or say out of 100 points. Okay, we're not looking at anything. I'm just explaining if you go to Blackboard, what the grades mean. Okay, so you can see that, okay, if I need to get a C-, I need this much on my final exam. But again, at the end of the everything, I do everybody's calculation to get everybody's grades. If a curving occurs, it's always in the direction of helping students with their grades. It's not going to be more harsh than the whatever established in the syllabus. So, so if curving occurs, is usually can bring up your score a little bit more. But this is what we're looking at. I'm just using 65, sort of a passing grade as we are right now. This is how much you need in the final. But again, you continue to have homework scores, you will continue to have pre-flights, all those will do a little bit more update to your those percentages. There is an end of the semester of post-assessment at the same It's roughly the same assessment you did at the beginning of the semester. So do that again, you'll get one more percent added onto your final grade. So that's just a breakdown of what we're looking at. I encourage you, all of you, take a look at your score. If anything doesn't look correct, make sure you let me know, okay? And any more questions, you can feel free to let me know, okay? All right, any other quick questions so far before we continue?
Is your grading scale on your syllabus?
It's on the syllabus, yes.
I have
Okay,
a
thank
question for the pre-flight. It says that it's due Monday, the 28th, but today is the 26th. So is it due on Wednesday or is it due today?
Oh, the one, let me take a look. Well, let's just make it, I will change it to Wednesday. We'll use whatever the later date as a deadline. So whatever it says, I'm gonna change it later after class to the Wednesday, okay?
Okay, thank you.
All right, so someone asked about the ENM2. I also wanted to make an announcement about that. The ENM2 is going to be an elective course, a second semester of ENM. It's going to be a continuation of this class. The format will be similar in the sense that we will have clicker questions, we have opportunity to discuss in class. We will have some tutorials, but we don't have a recitation activity session, right? The electives are only a 3-unit lecture course. So we won't have a 2-hour recitation every week. We may have some recitation we can do in class time, but it will be very brief. So not like what we have now. We will cover the rest of the Griffiths in the textbook. So that's what will be covered, a similar format, but there will be some differences from what ENM1 is. ENM1 is a required course, and also there's only one semester, right? So we have to make sure that we cover that much material. For example, I wanted to make sure I cover chapter 7 because that's where we get to time dependence before you have all statics. So if you want a full Maxwell equation, we need to include time dependence in the picture. So that sort of dictates our pace a little bit. We also sometimes need to rush. But with ENM2, with elective, I can assure you that we will be at a more relaxed pace in the sense if we need to slow down, we could, because it's all elective. We can decide the emphasis in the rest of the chapters, how much we want to focus on here or there. And also it will be a smaller classroom. So there will be much more opportunity for personal attentions with the instructor. So right now we have about 6 people enrolled. I want to encourage you, if you have an interest in this kind of line of topic, feel free to enroll. And we probably will need 10 for the class not to be canceled. Okay. For 10, I'm pretty confident that we're not canceled. For 6, I'm not so sure if we'll still keep it in the book. Okay, so a more relaxed pace, more focus with instructor. So don't be too worried if you feel like, I know ENM1 is a hard course, it's a core theory class for the physics majors. So don't be discouraged thinking, oh, if ENM1 is already hard, maybe ENM2 will be harder, and therefore I'm not going to take it. I don't want you to think that way. I want you to only think about, do you have an interest in the topic? Do you enjoy some of the concepts we discussed? If you do think so, I encourage you to enroll, okay? I believe, I don't want to go out and say grading will be more lenient, but as I have smaller enrollment, there's a lot more can be done, more attention and slowing down, more attention given to students who needed to catch up. So as a result of that, I believe the grading, the overall grades will be better than required a semester. So just ask yourself, if you feel an interest, you can enroll. If not, that's okay as well, of course. Okay, so that's all I'm going to say. A couple of announcements. Is the final cumulative? Thank you for asking that question. Okay, so final. Okay, I will upload the study guide, the example final, of course. It will not be cumulative. So you need to focus only on the new content to study for the final. That includes chapter 5, that's magnetostatics, where we did Biot-Savart and Ampere's law. And chapter 4 and 6, that's the ENM in matter, where you have polarization, electric displacement, and then later on we'll do magnetization and the H field. But chapter 4 and 6, we do it very quickly. So you can also expect they will account for a smaller portion in the final. So where we spend more time in class, we will do more, they will have a bigger portion in final. As well, the chapter 7 will be on the final as well. So it's chapter 5, 4, and 6, and then 7. It's not cumulative. So everything about chapter 1, 2, and 3 will not be included in the final. So just so that we have a little bit less to cover. There's a lot of topics. So we already tested the other ones. So let's just focus on the new content. All right. Any other questions? Okay, all right. So today I actually wanted to do a little bit recap. Before we do magnetic field and matter, I wanted to recap a little bit about what we did electric field and matter, because these two are a lot of similarity between them. So I believe the time we spent on summary and reviewing is not wasted. Make it easier when we go to the other topic. So let's do a little bit recap. Previously, we have discussed the polarization in the material. We use capital P to represent it. And do you still remember how polarization is defined?
Summation of dipole moments over something I forget.
Yes, summation of all the individual dipole moments over a volume. Very good. So that is polarization. It's in the same direction as your dipole moment. It's really just describing locally what is going on, right? You have all these little dipoles inside the material and they all line up in a certain way. And this is describing on average, what does that look like? And we also discussed when calculating potential of a material that's been polarized outside, we can look at the potential into two different part 1 and part 2. Part 1 is due to sigma bound. Part 2 is due to the charge density rho bound. So sigma bound, the bound surface current is defined to be, how is it related to polarization? Do you still remember that?
It's the charge that gets moved to the surface of your material when in the presence of an external.
Yes. So when these dipoles inside are being stretched apart, overall, if your polarization is uniform, overall inside is still with zero density, but on the surface you have these bound charges. So we have derived sigma is going to be equal to polarization, but you have to think about the direction. So end up to be P dot into N hat of the surface. Okay, so that is the bound surface density. We also talked about the if your polarization is no longer uniform, you will have volume bound charges, and these are defined to be negative, the divergence of your polarization. So these are bound volume density. Okay. Right, so if I give you polarization, you can evaluate, okay, what is the surface density and what is the bound volume density. We also did one example in class, but we didn't really finish it. So let's go ahead and finish that example because I think it's really nice. We can review some of the boundary conditions as well. The example is that if you have a sphere and you have certain polarization in this direction, that's uniform, right? So P is a constant that is in the Z direction. Okay, so this is my Z direction. So you can see that here we do not have bound volume charge because it's uniform, there's no divergence. So rho bound is 0. But it will have sigma bound. Sigma bound is P dot n hat, and we calculated it's end up to be P naught cosine theta because n hat is r hat, right? So this is r hat, this is theta. So the dot product gives you a cosine theta. And we borrow the example from Griffith's example 3.9. There we already find out what the potential is due to this kind of charge distribution, and they're exactly the same. So we went ahead and wrote out our potential for the inside of the sphere, inside and outside. So for inside, I'm gonna write out, sorry, inside first, inside is going to be P naught over 3 epsilon naught Z. V outside is P naught R cubed 3 epsilon naught R cosine theta. Okay, and then we can find the E field given the potential, right? So for inside, again, let's do the inside first. This is my V. Okay, so E is the negative gradient of V. So taking the gradient, right? So D, the gradient give you dV dx x hat, dV dy y hat, dV dz z hat. But you can see these are 0. It does not depend on x and y. So only thing left is the z direction. So it's going to be negative P naught over 3 epsilon naught. dz dz is 1 and in the z hat direction. So that is my electric field inside. So you can see inside this polarized sphere, the electric field is in this direction. Okay. This is my Z hat. We can do the outside as well, so we can complete the electric field for the sphere for outside. So I'm going to rewrite this outside again. We can refer back to that. 3 epsilon naught R cosine theta. Okay. For outside, ER is negative dV dr. So you can look up how to take the gradient in the spherical coordinates. And you can find out, well, ER is just the negative dV dr. E theta is 1 over R dV theta. So I can plug in this into individual equations and I can calculate ER and E theta. And this one does not have a phi because it doesn't have a phi dependence, right? So just R and theta hat. So the R becomes, you can see this becomes, sorry, did I miss? I think I missed the square. Okay. Yeah, you need the dimension to work out. You can see this is Z, or this is a dimension of the length. So this is R cubed, this kind of be R meter, R square. Okay, so I missed the square before. All right, add in that, we can find out for our electric field ER is going to be 2P naught R cubed cosine theta over 3 epsilon naught and R cubed. Okay, got a negative sign here, and then taking the derivative, you got a negative sign, so that's why here is positive. And do the theta hat direction, you simply gonna give you a negative sine theta. It's simply just gonna give you a sine theta. So you haven't 1 over r, so it's going to be r cubed. Negative sine theta, negative becomes positive sine theta. And this is 0. So I can write my E this way. 2 p naught r cubed over 3 epsilon naught r cubed 2 cosine theta. So this is ER is r hat, right? E theta theta hat. So this 2 cosine theta r hat plus sine theta theta hat. Okay. So this is your E for outside. Okay, so previously you recall how we draw this E field, right? We picked a few special points. For example, we can pick theta equals 0. Well, so when theta equals 0 is right here, right? Cosine theta is 1, sine theta is 0, so you're only going to end up with an r hat direction. So you know outside at this position, E is in the r hat direction, going out like that. Down here is going to be in this direction. And you can pick another point somewhere here. Here theta is pi over 2, right? When it's pi over 2, it's changed. Cosine pi over 2 is 0, and you're only going to have a theta hat. The theta hat is this direction. At that location, that's your theta hat, right? Because this will be my r hat, and theta hat is always perpendicular to your r hat. So overall, you can draw your electric field lines. It's going to be something like this outside. Okay, so this looks like a dipole field to you, right? This looks like a electric dipole field. So find your E inside and outside. One way to check, okay, did I get something correct? You can check to see whether the boundary conditions are met for at the surface of the sphere. So the boundary conditions, you can check for E parallel component, you can check for E perpendicular component. So let's do them one by one. So I'm going to do the parallel component first. Let's do the E parallel. E parallel across a boundary should be continuous, right? So E above a boundary should equal to E below the boundary, the parallel component of that. So let's check if that is true. Theta is pi over 2. When theta is pi over 2, E above. So E above is E outside. So above means it's outside, right? So outside we have this equation, and you plug in theta over pi over 2, you will get P naught R cubed 3 epsilon naught R cubed. Okay. The reason I chose this because that gives you the parallel component, right? This is your surface. When you're here, the E is parallel to the surface. That is the parallel component of E. Okay, so we evaluate it at this location. It's going to give you this value. P naught, this cancels over 3 epsilon naught. And we know what direction it is. You can see that, well, it's theta hat. In that particular location, theta hat is negative Z. So you can put negative Z in there. What about E parallel below the boundary? Below the boundary is inside, right? Inside. Inside, you already calculate your E to be this. So E inside, well, is going to be negative P naught over 3 epsilon naught Z hat, is indeed equal to my above at the boundary, right? E above at R equals out. At R equals out, they're equal. So I have checked my boundary conditions and the parallel component is indeed equal. one last thing to do is to check the perpendicular component. So where do I find the perpendicular component? You can see here is my surface. This is perpendicular to the boundary. So this is my perpendicular component. And are they indeed going to give me the boundary conditions, which is above perpendicular minus below perpendicular is sigma over epsilon naught. So let's see. So at theta equals 0, you get your perpendicular component. So E outside is the E above. At R equals R, theta is 0. So it's here, plug in theta equals 0 and R equals R. You got a capital R here, you got a 1 here. So 2 becomes T naught R cubed. Oh, theta equals 0. Yeah. Did I have a 2? I don't have a 2 here. I already took 2 outside my integral. Sorry, don't have a 2 here. Okay, so I get 2R hat 3 epsilon naught R cubed. Okay, that R hat is in the Z hat direction, right? So you can replace that with Z hat. So it's 2 P naught over 3 epsilon naught Z hat. Okay, now let's do the below. Below is this guy, negative P naught over 3 epsilon naught Z hat. Because that's inside we already calculated is here. So it's this guy. Okay, so do they indeed match up with your boundary conditions? Let's see. You use the above minus the below, E above minus E below at the boundary, of course. All of this means at the boundary, but we don't always write it out, but you should know it's applied at the boundary. Is going to be this minus this. What does that become? It becomes 3 P naught over 3 epsilon naught. And that gives me P naught over epsilon naught. Okay. And that equal to sigma over epsilon naught. Is that right? Sigma over epsilon naught. So is this condition met? Is P naught equal to epsilon naught? Epsilon? What is this sigma? Sorry, what is this bound? What is the surface density? This is the surface charge here at the boundary. And what kind of surface charge do we have? Where does it come from?
It's coming from your polarization.
Yes, it's coming from my polarization, right? So indeed, this is sigma bound, the polarization, as I have positive on top, negative polarization, a negative charge on the bottom. So sigma is the surface at the surface charge, the bound surface charge density is indeed sigma bound is equal to polarization P naught. So they are indeed equal. And I have checked my second boundary condition is also met, making sure that, okay, I know that I did my calculation correct. I didn't make any mistakes. So it's something you can always check to see that if that's true. All right. Okay,
Could you explain again why they're equal? Sorry.
Why this is equal? Recall that bound surface density is polarization, right? Sigma is always equal to P. This just gives you directions.
Okay, I see.
Okay, so this is something we derived in our previous lecture notes. Okay. And further, after we did polarization, we did displacement. We defined, so this is another review for our displacement field. Displacement field D how do we define it? Is going to be epsilon naught E plus polarization P. Okay, so that is a displacement field. And also the Gauss's law for your D field is dA is Q free enclosed, Q free. Okay. Oftentimes it's easier to calculate D first because free charges are, we know what it is, right? We know what free charges, we don't always know what the bound charges are. But since you have this relationship and if your material is linear, P is also proportional to E. So epsilon naught chi times E. P is always in the same direction as your E field. So with that information, you can, given any of these quantities, you can calculate the other. D becomes this plus P. So I'm going to plug in this on my P. 1 plus chi, and we call this epsilon R, which is the dielectric constant of the material. This one does not have unit. Okay. This is sigma naught, sigma R. This one has unit, the same unit as sigma naught, permittivity of the dielectric. Epsilon R does not have unit. Okay, it's just a number. All right, so which means, okay, I can write my D simply saying epsilon times E. Polarization is this proportional to your E field. You can also, if you know your D field, you can also write it using your B field. So they're all related. Times 2. So anything that you give one, you will be able to find the other. So we did an example in class, and it looks like a capacitor, right? We inserted some dielectric material inside the capacitor. What we did was, we have a parallel plate, metals, these two are metals, right? These are your external field. Then you put a dielectric material inside. It's going to be polarized, right? Because when you polarize, you're going to have some positive charges on the top surface, and negative charges on the bottom surface, right? And my polarization is in the same direction as P. Remember, P is also up from negative charge to positive charge. That's the dipole moment, polarization up. Okay. But think about this, the actual E field. So these charges, the E field, induced E field is from positive to negative. So E induced is going down. Okay, so you can see as a result of that, E total is still pointing up, but is weaker, is now weaker due to the dielectric material inserted inside the capacitor. Sigma, so you can see this is your sigma bound on the top, right? Negative sigma bound on the bottom. This is equal to your polarization. Negative. Sigma total. So you can calculate your E field by saying, okay, if I draw a Gaussian cylinder here at the surface, right? You can see I'm enclosing both the free charge and the bound charge. So the total is going to be sigma free minus sigma bound. Or here it looks like it's the bottom. So sigma free minus sigma bound. Sigma free is just sigma. Sigma bound is equal to your polarization. And what is your polarization? Your polarization is this times D. And do you still recall how we did D? D is equal to sigma free, right? This is one of our quicker questions. Q free, right? D times 4 pi r squared. No, it's just the area. Q free is sigma free times area. So D is just sigma. So my P is chi over 1 plus chi sigma free. And you can see as a result of this, this is sigma over 1 plus chi E, which is sigma over epsilon r. So you can see as a result of this, your total charge is your original charge, free charge, reduced by a factor of sigma, epsilon r. Sorry, there are too many constants. I keep saying the wrong thing. But, so you can see this is reduced by 1 over epsilon r. Okay, so your E field is also reduced by the same factor, right? Because for E, oops, sorry. It looks like I need to connect my pen a little bit, but let me connect my pen. I just wanted to talk about the meaning of this. Your E field is can be calculated by looking at the total charge enclosed, including free and bound charge. So for Gauss's law, you should remember for a surface charge, E field is sigma over 2 epsilon naught using Gauss's law. So if the surface density is reduced, now your E field is also reduced. So that's why we say we like to insert dielectric material in our capacitor because it gives me a weaker E field. Giving a particular potential, it have a weaker E field, is less likely to break down. It can also give me a bigger capacitance. It will have a more stored energy in the capacitor. Okay. All right. So this is a review I want to do. Now let's go back to our new topic. Okay. New topic is magnetization and bound currents. So I want to show you that once we have done what we did previously, these will be very similar. So polarization, right, is arrived from little dipole moments inside the material. So here, you know what an electric dipole is. What would be a magnetic dipole? We know what electric charge is. We know what electric monopole is. It's just a point charge, a charge. Do we have a magnetic monopole?
No.
We don't. So it's really just, well, we can't, but we do have a magnetic dipole. So what is a magnetic dipole?
An object with a north and south facing side.
Yes, exactly. So we can define, here we're talking about using the currents when we discuss the magnetic field. So what would produce a magnetic dipole is if you have a current that's simply in this direction, like a current loop, for example, then this will give you a magnetic dipole moment pointing upward. Okay? So this is equivalent of seeing you have a magnet with a north pole and south pole, right? Where your field lines coming like this. And this is sort of similar to that, right? You can view this on the up to be the north pole, the below is the south pole. And this is a magnetic dipole. And a dipole moment M, as you recall, is going to be current I times the area of this is just uniform for current, uniform across this area is going to be current times the area vector. Okay, so it's in the direction pointing upward in the direction of following a right-hand rule of your current. So the current is counterclockwise, the dipole moment is pointing upward. So that is a magnetic dipole moment. So magnetization is if your material is being magnetized. Previously, we say if your material is being polarized, then polarization P is all the little dipole moment divided by volume. So you can pretty much guess how are we going to define the magnetization. So what would the magnetization be?
Summation of dipole moments all over your volume.
Yes. So it's sum of the magnetic dipole moments over the volume. And this is magnetization of the material. So just as in chapter 4, we start out with, okay, the potential due to the dipole field. Here we can write our vector potential due to dipole moment. So I'm going to quote Griffiths 5.85, the equation for calculating the potential due to a dipole moment. So A due to a magnetic dipole is equal to mu naught over 4 pi dipole moment cross squared r hat over r squared. Okay, so here we know that m, little m, is capital M magnetization in. Now, if you're talking about one dipole moment, that is a small chunk of material inside your entire the material that's been magnetized. Right. So if you look at the little chunk is d tau, that's the volume times magnetization, you get a little dipole moment. Overall, you can say, what about you add up all those little chunks, you have the A due to the entire object, then you need to integrate everything. So if you do the integration, it becomes capital M cross R hat over R squared d tau. Okay, right? Because if you integrate this, you get the total dipole moment. So this is a total. Okay, so you probably also recall what we're going to do here. What we had there, we artificially make this into two different parts. Is V due to sigma bound and V due to rho bound. You have some. You can view the process of polarization into generating some current, generating some surface density, generating some volume density, and those charges are going to give you potential. Here, we're going to do the exact same thing. We're going to manipulate this expression into two different parts, and we can give physical meanings to each part. So after some math, you can look at page 264 in your textbook for the proof. The process, after you do this manipulation, A can be rewritten into two parts. The first part is due to current, okay, surface current, call this bound current. The second part is, you probably will guess what it is. Surface current, now it's volume current, right? Is J bound. So this is, so the process of the magnetization, you can view this, okay, the magnetic field produced by this material that's being magnetized is equivalent to viewing there's some surface current producing the magnetic field, there's some volume current producing the magnetic field, okay? And K is related to polarization. So previously, so sigma bound is equal to P polarization. You add the direction. Here, K bound is equal to magnetization, and you added the direction. So it's a cross product between M and N hat. Again, there, sorry, not J. rho is divergence of P. Here, J bound is the curl of M. So that's how we have found the bound current and the volume current. We will, of course, later on talk about why are they equal. We'll go through the derivation again. But this is, you can see we follow a very similar strategy as we did previously. Okay, now let's look at the bound current. So how come a magnetization is equivalent of producing some bound currents? Okay. After we do that little bit derivation, we will be able to do some questions on our own, but let's first look at the physical meaning of this term. So these bound currents are these imaginary, or they have the same effect or effective currents, bound currents that generate the magnetic field. So we call them imaginary because, you know, it's not, you really run current through them, right? It's as an effect, it's as if there are some magnetic field being produced by the currents due to magnetization. So a magnetizing object, they acted like it had these ordinary current flowing in it. So let's look at an object that's been magnetized. So we consider a small chunk of material that has been magnetized. With magnetization M in the volume, right? So just gonna say dx dy dz. So magnetization is magnetic moment divided by volume. So I mean, define our x and y z like this. So let's draw this little chunk. You have a little chunk. And let's just say our magnetization or our magnetic dipole moment pointing in the z direction. And each of these legs, this is the x, this is the z, and this is dy. Okay. And you can see there are magnetization, right? Which means there are some bound currents going, there are some currents going through it. So let me draw these little currents. So following the right-hand rule, you see your M is pointing in the Z, so your 4 fingers wraps around. So each of the little chunk is being magnetized. So you can view this as if you have the M arise from the currents running around like this. So M is dipole moment is current times area, we call the definition. So here, we're going to plug in current and the area for such a situation. You can see that it looks like you have the surface current on all the 4 surfaces, right? So you have some surface current K here on the surface, you have some surface current here on the surface. So I is K times L perpendicular. So what is my L perpendicular here? So you can see the surface current is running across this leg. The surface current is running across this L. This is your L perpendicular. So on my diagram, what is L perpendicular? Is it the X, the Y, or the Z?
dx.
Why? Okay, let me draw this a little bit better. Okay. This is my surface current. Should be perpendicular. perpendicular to this leg. And what is this leg?
Should be DZ then.
It is dz, yes. So it's going to be k dz. Okay, current is k dz. And what about the area? This is the area I'm looking at. This area? I'm sorry, go ahead, sorry. This is my dipole moment and this is my area.
Dx dy.
Yeah, it's dx dy. Okay, so it's going to be k dx dy dz. Recall the magnetization is defined to be m over volume. Right? So it's going to be m over dx dy dz. So if you plug in here, you get k. Right? So magnetization is equal to surface bound surface current. So in terms of their magnitude, they are equal. They have the same magnitude. Okay. This is similar to how we derive sigma equals P, right? But you also have the directions. So we have to figure out if the directions is indeed m cross n hat. Okay, so let's look at one of the surfaces, for example. The directions of K. The surface bound currents, you can see that I have many little chunks inside my material. Each of the chunk is like a little magnetic dipole moment. So if I'm going to draw a few little chunks like this. Right, this is a little chunk within the magnetized material that you have a dipole moment here, you have a dipole moment here, you have a dipole. You can see that overall, it's equivalent to having this entire material with a surface of current running through the surface, right? So on the bottom, right, and go up, and then to the left, and then go down. Right, in between them, they cancel because this one is to the left, and this one is to this one to the right, this one to the left. Inside they cancel, but overall on the surface, it does not cancel. So overall, you end up with this bound surface current. So if I look at, I'm going to sort of extend these a little bit. This is a little volume. And recall what we have on each of these legs. This is the X, and this was my dz, right? And going upward, that's my dy. Okay, so I'm going to look at the current here that's running in the X direction, right? Because you can see surface current is in many different directions at different surfaces. I want to be able to show you this. I'm going to pick one particular surface. So I'm going to pick the bottom surface. For the bottom surface, in what direction is your K? K is running in the X direction, right? This is my X direction. And in what direction is my M cross N hat? Are they really equal to each other? So on the bottom surface, this is my bottom surface that I draw here. What is your N hat? The XZ plane. The bottom surface is the XZ plane. The N hat, so the XZ plane is pointing directly downward. And that is what direction?
Minus dy.
Minus y hat. Very good. Minus y hat. Downward is minus y. And what about my N? Remember, my polarization is in this direction. And that is your Z, right? That is your Z. So M is in z direction. Okay, n is in y hat, m is in z. So when you do m cross n hat, you got z cross y hat, negative y hat. That gives you negative z cross y is a negative x hat, negative, negative give you positive x hat. So indeed, m cross n hat for the bottom surface is in the same direction as my surface, bound surface current density. So therefore we said, okay, it looks like we can describe our K using magnetization across the area vector for the particular surface you're looking at. Okay, all right, so that's a lot of derivation. So hopefully now we are ready to answer some questions. First question is regarding the definition of magnetization. So here I'm showing you a solid cylinder with a uniform magnetization M throughout this entire volume. What is the magnitude of the total magnetic dipole moment? So for this one, I believe we don't really need to discuss, so I will go ahead and open up the poll for you. All right, 10 more seconds. If you haven't voted already, please put in your vote. All right, let's take a look. I'm gonna close this. All right, you can see a direct application of your definition. Very good. So A is correct. You simply need to multiply the magnetization, which is uniform, times the entire volume of the cylinder, right? Which is the surface area, the top and bottom times the height. Very good. Let's look at another question. Here we have a magnetization throughout the volume, but now magnetization is upward. This part is pointing in the z direction. So where do the bound currents show up? Okay, I want to recall K bound is M cross N hat. J bound is the curl of M. So this one, I will open up breakout rooms for you to discuss. And after we discuss, we'll come back to vote. All right, 10 more seconds. All right, let's take a look at this together. Where do the bound currents show up? Okay. All right. So there could be two kind of bound currents, volume bound current or the surface current. So which one do you think we have, or do we have both? We have the bound volume current for this kind of magnetization. Do we have a non-zero curl for M? M is uniform, pointing upward. The curl of M, zero or non-zero?
I mean, it should be not. It should be 0.
Yes, it is a zero curl. No trap there. It's uniform. There's no, you can see that uniform, there's no divergence and also no curl. Okay? So there's no bound currents running through the volume. So there's only surface currents on the surface. And for a cylinder, right, you can describe the different surfaces using different directions. So for the top and the bottom surface, this n hat is z hat direction. Okay, m is in the z hat direction. Okay, so for the top surface, z hat cross c hat is going to be 0. So there's not going to be any current in the top and the bottom surface. So there's also the side surface. For the cylinder, the barrel, the side surface is n hat. So what notation do we describe? How do we describe this direction?
R hat or
Yes.
S hat.
Yes, R hat or
Very good.
S hat. Very good. So do you think what will we have if we use a z hat, which is m, cross a s hat?
You'll get 1.
So,
Sorry, 1 times the sine of theta.
so first for Cartesian, right? I remember x cross y give me z, y cross c give me x, z cross x give me y. So for cylindrical, it's the same idea. Z cross s give me phi hat. Okay. S cross phi give me z hat. So z cross f, s is a phi hat direction. So I know I do have bound surface current and they're on the side surface only. So yes, C is correct. They're running in the phi hat direction. So you can see if this makes sense to you, if your bound currents and we say is in the phi hat direction. Okay, so if you have those currents running in that direction, what kind of B field is going to give you in what direction? Your currents are curling around. If the forefinger is curling around, you have a B field pointing in.
The same direction as your magnetization.
Yes. So the idea is if you have such a magnet, right, it's producing a B field pointing upward. And then if you have, this is equivalent of having bound surface current. If you have current, it's also producing a B field that's upward. So it's showing that these are equivalent effects, right? So it's on the side surface only. So a little bit discussion. So let's discuss this. We just said this is equivalent to the bound surface current. We have the uniform magnetization running through pointing upward. The B field will look like. Now consider these two extremes. If your cylinder is extremely tall and thin, or if your cylinder is very short and fat separately. So if your cylinder is tall and thin, what do you think the B will look like? This is equivalent of having the bound current in this. This is a thin and tall cylinder. I have bound current going in this way. What does this look like to you? What does this look like?
It looks like a conducting wire.
What about them wrapping around many rounds?
Oh, a solenoid.
Yes. Okay. So tall and thin is like a solenoid, and what would B look like?
A single plate of a capacitor.
Yes, like a capacitor in the sense it's uniform inside. It's uniform upward and a constant inside the cylinder and zero outside. Very good. Now, what if this very short and fat, super short, is kind of reduced to just a bound current going this way? This is the second extreme, really short. So what would B look like there?
So a disc or a single plate of a capacitor.
Yeah, this is like a current carrying loop, whereas where your B is going to be. Okay, so these are just two extremes. We can think about the effectiveness of such a magnetization by thinking, what if we reduce them to bound currents, right? If them are really thin and tall, like an infinite solenoid, your B will be just upward and also uniform. But if it's really short, you can see that it looks like a loop, because your B is not going to be uniform and curls around away from the center. All right. Okay, so that's all we're going to do for today. On Wednesday, we will do the rest of the discussion on the volume current, volume bound current, and we can calculate and see some examples of how to calculate it. Okay, so I will see you guys on Wednesday. Again, please check your grade estimate. Make sure the exam scores are showing up properly, your pre-quiz and your homework. And if you see anything that's inconsistent, please let me know. All right. Have a good rest of the day. I'll see you on Wednesday.
Thank you, Dr. Ryan.
Thank you. Bye-bye.